Science is a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. Contemporary science is typically subdivided into the natural sciences, which study the material universe, the social sciences, which study people and societies, and the formal sciences, such as mathematics. The formal sciences are often excluded as they do not depend on empirical observations. Disciplines which use science like engineering and medicine may also be considered to be applied sciences. During the Middle Ages in the Middle East, foundations for the scientific method were laid by Alhazen in his Book of Optics. From classical antiquity through the 19th century, science as a type of knowledge was more closely linked to philosophy than it is now, and, in fact, in the Western world, the term natural philosophy encompasses fields of study that are today associated with science, such as astronomy, medicine, and physics, while the classification of the material world by the ancient Indians and Greeks into air, earth, fire and water was more philosophical. Medieval Middle Eastern scientists used practical, experimental observation to classify materials. In the 17th and 18th centuries, scientists increasingly sought to formulate knowledge in terms of laws of nature. Over the course of the 19th century, the word science became increasingly associated with the scientific method itself, as a disciplined way to study the natural world. It was in the 19th century that scientific disciplines such as biology, chemistry, and physics reached the modern shapes. The same time period also included the origin of the terms scientist and scientific community, the founding of scientific institutions, and increasing significance of the interactions with society and other aspects of culture. History. Science in a broad sense existed before the modern era and in many historical civilizations. Modern science is distinct in its approach and successful in its results. Modern science now defines what science is in the strictest sense of the term. Science in its original sense is a word for a type of knowledge, rather than a specialized word for the pursuit of such knowledge. In particular, it is one of the types of knowledge which people can communicate to each other and share. For example, knowledge about the working of natural things was gathered long before recorded history and led to the development of complex abstract thinking. This is shown by the construction of complex calendars, techniques for making poisonous plants edible, and buildings such as the pyramids. However, no consistent conscientious distinction was made between knowledge of such things which are true in every community and other types of communal knowledge, such as mythologies and legal systems. Antiquity before the invention or discovery of the concept of nature by the pre-Socratic philosophers. The same words tend to be used to describe the natural way in which a plant grows, and the way in which, for example, one tribe worships a particular god. For this reason it is claimed these men were the first philosophers in the strict sense, and also the first people to clearly distinguish nature and convention. Science was therefore distinguished as the knowledge of nature and the things which are true for every community, and the name of the specialized pursuit of such knowledge was philosophy, the realm of the first philosopher-physicists. They were mainly speculators or theorists particularly interested in astronomy. In contrast, trying to use knowledge of nature to imitate nature was seen by classical scientists as a more appropriate interest for lower-class artisans. A clear-cut distinction between formal and empirical science was made by pre-Socratic philosopher Parmenides. Although his work Periphraseos is a poem, it may be viewed as an epistemological essay, an essay on method in natural science. Parmenides words new may refer to a formal system, a calculus which can describe nature more precisely than natural languages. Physics may be identical to new. A major turning point in the history of early philosophical science was the controversial but successful attempt by Socrates to apply philosophy to the study of human things, including human nature, the nature of political communities, and human knowledge itself. He criticized the older type of study of physics as too purely speculative and lacking in self-criticism. He was particularly concerned that some of the early physicists treated nature as if it could be assumed that it had no intelligent order, explaining things merely in terms of motion and matter. The study of human things had been the realm of mythology and tradition, and Socrates was executed. Aristotle later created a less controversial systematic program of Socratic philosophy, which was teleological and human-centered. He rejected many of the conclusions of earlier scientists. For example, in his physics the sun goes around the earth, and many things have it as part of the nature that they are for humans. Each thing has a formal cause and final cause and a role in the rational cosmic order. Motion and change is described as the actualization of potentials already in things, according to what types of things they are. While the Socratics insisted that philosophy should be used to consider the practical question of the best way to live for a human being, they did not argue for any other types of applied science. Aristotle maintained the sharp distinction between science and the practical knowledge of artisans, treating theoretical speculation as the highest type of human activity, practical thinking about good living as something less lofty, and the knowledge of artisans as something only suitable for the lower classes. In contrast to modern science, Aristotle's influential emphasis was upon the theoretical steps of deducing universal rules from raw data, and did not treat the gathering of experience and raw data as part of science itself. Medieval science during late antiquity and the early Middle Ages, the Aristotelian approach to inquiries on natural phenomena was used. Some ancient knowledge was lost, or in some cases kept in obscurity, during the fall of the Roman Empire and periodic political struggles. However, the general fields of science, or natural philosophy, as it was called, and much of the general knowledge from the ancient world remained preserved, though the works of the early Latin encyclopedists like Isidore of Seville. Also, in the Byzantine Empire, many Greek science texts were preserved in Syriac translations done by groups such as Nestorians and Monophysites. Many of these were translated later on into Arabic under the Caliphate, during which many types of classical learning were preserved and in some cases improved upon. The House of Wisdom was established in Abbasid era Baghdad, Iraq. It is considered to have been a major intellectual center during the Islamic Golden Age, where Muslim scholars such as Al-Kindan ibn Sahl in Baghdad, and Ibn al-Haytham in Cairo, flourished from the 9th to the 13th centuries, until the Mongol sack of Baghdad. Ibn al-Haytham, known later to the West as Al-Hasan, furthered the Aristotelian viewpoint by emphasizing experimental data. In the later medieval period, as demand for translations grew, for example from the Toledo school of translators, Western Europeans began collecting texts written not only in Latin, but also Latin translations from Greek, Arabic, and Hebrew. The texts of Aristotle, Ptolemy, and Euclid, preserved in the Houses of Wisdom, were sought amongst Catholic scholars. In Europe, Al-Hasan's De Aspectibus directly influenced Roger Bacon in England, who argued for more experimental science, as demonstrated by Al-Hasan. By the late Middle Ages, a synthesis of Catholicism and Aristotelianism known as scholasticism was flourishing in Western Europe. which had become a new geographic center of science, but all aspects of scholasticism were criticized in the 15th and 16th centuries. Renaissance and early modern science. Medieval science carried on the views of the Hellenist civilization of Socrates, Plato, and Aristotle, as shown by Alhazen's last work, a book in which I have summarized the science of optics from the two books of Euclid and Ptolemy, to which I have added the notions of the first discourse, which is missing from Ptolemy's book from Ibn Abi Eusebia's catalogue, as cited in. Alhazen conclusively disproved Ptolemy's theory of vision, but Alhazen retained Aristotle's ontology. Roger Bacon, Witello, and John Peckham each built up a scholastic ontology upon Alhazen's book of optics, a causal chain beginning with sensation, perception, and finally apperception of the individual and universal forms of Aristotle. This model of vision became known as perspectivism, which was exploited and studied by the artists of the Renaissance. Mark Smith points out the perspectivist theory of vision is remarkably economical, reasonable, and coherent, which pivots on three of Aristotle's four causes: formal, material, and final. Although Alhazen knew that a scene imaged through an aperture is inverted, he argued that vision is about perception. This was overturned by Kepler, who modeled the eye with a water-filled glass sphere, with an aperture in front of it to model the entrance pupil. He found that all the light from a single point of the scene was imaged at a single point at the back of the glass sphere. The optical chain ends on the retina at the back of the eye and the image is inverted. Copernicus formulated a heliocentric model of the solar system, unlike the geocentric model of Ptolemy's Almagest. Galileo made innovative use of experiment and mathematics. However, his persecution began after Pope Urban VIII blessed Galileo to write about the Copernican system. Galileo had used arguments from the Pope and put them in the voice of the simpleton in the work Dialogue concerning the two chief world systems, which caused great offense to him. In Northern Europe, the new technology of the printing press was widely used to publish many arguments, including some that disagreed with church dogma. René Descartes and Francis Bacon published philosophical arguments in favor of a new type of non-Aristotelian science. Descartes argued that mathematics could be used in order to study nature, as Galileo had done, and Bacon emphasized the importance of experiment over contemplation. Bacon questioned the Aristotelian concepts of formal cause and final cause, and promoted the idea that science should study the laws of simple natures, such as heat, rather than assuming that there is any specific nature, or a formal cause, of each complex type of thing. This new modern science began to see itself as describing laws of nature. This updated approach to studies in nature was seen as mechanistic. Bacon also argued that science should aim for the first time at practical inventions for the improvement of all human life. Age of Enlightenment. In the 17th and 18th centuries, the project of modernity, as had been promoted by Bacon and Descartes, led to rapid scientific advance and the successful development of a new type of natural science, mathematical, methodically experimental, and deliberately innovative. Newton and Leibniz succeeded in developing a new physics, now referred to as Newtonian physics, which could be confirmed by experiment and explained using mathematics. Leibniz also incorporated terms from Aristotelian physics, but now being used in a new non-teleological way, for example, energy and potential. In the style of Bacon, he assumed that different types of things all work according to the same general laws of nature. with no special formal or final causes for each type of thing. It is during this period that the word science gradually became more commonly used to refer to a type of pursuit of a type of knowledge, especially knowledge of nature, coming close in meaning to the old term natural philosophy. 19th century, both John Herschel and William Whewell systematized methodology. The latter coined the term scientist. When Charles Darwin published On the Origin of Species, he established descent with modification as the prevailing evolutionary explanation of biological complexity. His theory of natural selection provided a natural explanation of how species originated, but this only gained wide acceptance a century later. John Dalton developed the idea of atoms. The laws of thermodynamics and the electromagnetic theory were also established in the 19th century, which raised new questions which could not easily be answered using Newton's framework. The phenomena that would allow the deconstruction of the atom were discovered in the last decade of the 19th century. The discovery of X-rays inspired the discovery of radioactivity. In the next year came the discovery of the first subatomic particle, the electron. 20th century and beyond, Einstein's theory of relativity and the development of quantum mechanics led to the replacement of Newtonian physics with a new physics which contains two parts that describe different types of events in nature. In the first half of the century, the development of artificial fertilizer made possible global human population growth. At the same time, the structure of the atom and its nucleus was elucidated, leading to the release of atomic energy. In addition, the extensive use of scientific innovation, stimulated by the wars of this century, led to antibiotics and increased life expectancy. Revolutions in transportation, and the development of ICBMs, a space race, and a nuclear arms race, all giving a widespread public appreciation of the importance of modern science. Widespread use of integrated circuits in the last quarter of the 20th century, combined with communications satellites, led to a revolution in information technology, and the rise of the global internet and mobile computing, including smartphones. More recently, it has been argued that the ultimate purpose of science is to make sense of human beings and our nature. For example, in his book Consilience, E.O. Wilson said, "The human condition is the most important frontier of the natural sciences. The scientific method seeks to explain the events of nature in a reproducible way. An explanatory thought experiment, a hypothesis, is put forward as explanation, using principles such as parsimony and are generally expected to seek consilience, fitting well with other accepted facts related to the phenomena. This new explanation is used to make falsifiable predictions that are testable by experiment or observation. The predictions are to be posted before a confirming experiment or observation is sought, as proof that no tampering has occurred. Disproof of a prediction is evidence of progress. This is done partly through observation of natural phenomena, but also through experimentation that tries to simulate natural events under controlled conditions, as appropriate to the discipline. Experimentation is especially important in science to help establish causal relationships. When a hypothesis proves unsatisfactory, it is either modified or discarded. If the hypothesis survived testing, it may become adopted into the framework of a scientific theory. This is a logically reasoned, self-consistent model, a framework for describing the behavior of certain natural phenomena. A theory typically describes the behavior of much broader sets of phenomena than a hypothesis. Commonly, a large number of hypotheses can be logically bound together by a single theory. Thus a theory is a hypothesis explaining various other hypotheses. In that vein, theories are formulated according to most of the same scientific principles as hypotheses. In addition to testing hypotheses, scientists may also generate a model based on observed phenomena. This is an attempt to describe or depict the phenomenon in terms of a logical, physical or mathematical representation and to generate new hypotheses that can be tested. While performing experiments to test hypotheses, scientists may have a preference for one outcome over another, and so it is important to ensure that science as a whole can eliminate this bias. This can be achieved by careful experimental design, transparency, and a thorough peer review process of the experimental results as well as any conclusions. After the results of an experiment are announced or published, it is normal practice for independent researchers to double-check how the research was performed, and to follow up by performing similar experiments to determine how dependable the results might be. Taken in its entirety, the scientific method allows for highly creative problem-solving while minimizing any effects of subjective bias on the part of its users. Mathematics and formal sciences. Mathematics is essential to the sciences. One important function of mathematics in science is the role it plays in the expression of scientific models. Observing and collecting measurements, as well as hypothesizing and predicting, often require extensive use of mathematics. Arithmetic, algebra, geometry, trigonometry, and calculus, for example, are all essential to physics. Virtually every branch of mathematics has applications in science, including pure areas such as number theory and topology. Statistical methods, which are mathematical techniques for summarizing and analyzing data, allow scientists to assess the level of reliability and the range of variation in experimental results. Statistical analysis plays a fundamental role in many areas of both the natural sciences and social sciences. Computational science applies computing power to simulate real-world situations, enabling a better understanding of scientific problems than formal mathematics alone can achieve. According to the Society for Industrial and Applied Mathematics, computation is now as important as theory and experiment in advancing scientific knowledge. Whether mathematics itself is properly classified as science has been a matter of some debate. Some thinkers see mathematicians as scientists, regarding physical experiments as inessential or mathematical proofs as equivalent to experiments. Others do not see mathematics as a science, since it does not require an experimental test of its theories and hypotheses. Mathematical theorems and formulas are obtained by logical derivations which presume axiomatic systems, rather than the combination of empirical observation and logical reasoning that has come to be known as the scientific method. In general, mathematics is classified as formal science, while natural and social sciences are classified as empirical sciences. Scientific community. The scientific community is the group of all interacting scientists. It includes many sub-communities working on particular scientific fields, and within particular institutions. Interdisciplinary and cross-institutional activities are also significant. Branches and fields. Scientific fields are commonly divided into two major groups: natural sciences, which study natural phenomena, and social sciences, which study human behavior and societies. These groupings are empirical sciences, which means the knowledge must be based on observable phenomena and capable of being tested for its validity by other researchers working under the same conditions. There are also related disciplines that are grouped into interdisciplinary applied sciences, such as engineering and medicine. Within these categories are specialized scientific fields that can include parts of other scientific disciplines but often possess their own nomenclature and expertise. Mathematics, which is classified as a formal science, has both similarities and differences with the empirical sciences. It is similar to empirical sciences in that it involves an objective, careful and systematic study of an area of knowledge. It is different because of its method of verifying its knowledge, using a priori rather than empirical methods. The formal sciences, which also include statistics and logic, are vital to the empirical sciences. Major advances in formal science have often led to major advances in the empirical sciences. The formal sciences are essential in the formation of hypotheses, theories, and laws, both in discovering and describing how things work and how people think and act. Apart from its broad meaning, the word science sometimes may specifically refer to fundamental sciences alone. Science schools or faculties within many institutions are separate from those for medicine or engineering, which is an applied science. Institutions, learned societies for the communication and promotion of scientific thought and experimentation have existed since the Renaissance period. The oldest surviving institution is the Italian Accademia.dei Linke, which was established in 1603. The respective national academies of science are distinguished institutions that exist in a number of countries, beginning with the British Royal Society in 1660 and the French Académie des Sciences in 1666. International scientific organizations, such as the International Council for Science, have since been formed to promote cooperation between the scientific communities of different nations. Many governments have dedicated agencies to support scientific research. Prominent scientific organizations include the National Science Foundation in the U.S., the National Scientific and Technical Research Council in Argentina, the Academies of Science of many nations, CSIRO in Australia, Centre National de la Recherche Scientifique in France, Max Planck Society and Deutsche Forschungsgemeinschaft in Germany, and in Spain, CSIC. Literature. An enormous range of scientific literature is published. Scientific journals communicate and document the results of research carried out in universities and various other research institutions, serving as an archival record of science. The first scientific journals, Journal des Sçavans followed by the Philosophical Transactions, began publication in 1665. Since that time, the total number of active periodicals has steadily increased. In 1981, one estimate for the number of scientific and technical journals in publication was 11,500. The United States National Library of Medicine currently indexes 5,516 journals that contain articles on topics related to the life sciences. Although the journals are in 39 languages, 91% of the indexed articles are published in English. Most scientific journals cover a single scientific field and publish the research within that field. The research is normally expressed in the form of a scientific paper. Science has become so pervasive in modern societies that it is generally considered necessary to communicate the achievements, news, and ambitions of scientists to a wider populace. Science magazines such as New Scientist, Science and Empirical, and Scientific American cater to the needs of a much wider readership and provide a non-technical summary of popular areas of research, including notable discoveries and advances in certain fields of research. Science books engage the interest of many more people. Tangentially, the science fiction genre, primarily fantastic in nature, engages the public imagination and transmits the ideas, if not the methods, of science. Recent efforts to intensify or develop links between science and non-scientific disciplines such as literature or, more specifically, poetry, include the Creative Writing Science resource developed through the Royal Literary Fund.